Hi, good evening. My name is Mr. Manoj and I'm going to help you to understand the main questions which has come in May 2013, paper 22. This is AS Chemistry, syllabus 9701. Hopefully I'm going to make more videos of this sort. You probably might get some help from me. Now the first question talks about, the question says, describe what you mean by a weak base. Now, by definition, bases are proton acceptors, we know that. So you could, since this is a 3-mark question, you could always, of course, start with a good definition, and you could say, being a weak base is a poor proton acceptor, so that would give you the first mark. It's a poor proton acceptor, that should give you the first mark. And the question says you must use ammonia to explain your answer. So you could always go for an equation in which ammonia, you show ammonia gaining a proton. When ammonia gains a proton, it changes into an ammonium ion. You could look up your topic 3 of your syllabus, where you study the structure of ammonia. You know ammonia, nitrogen has a lone pair of electrons, and that helps us to connect with the proton with a dative bond to form ammonium. So if you write an equation, that should give you 1 mark, and the definition stating that it's a poor proton acceptor is worth 1 mark. And if you show in this equation the reversible sign, then that's worth 1 mark. So that's usually how the 3 marks are given. This is for the first question, C part. The compound given is Cl, CH2, CHOH, CH2Cl. And the question says, what do you think will be produced when this compound reacts with concentrated sulfuric acid? Now, if you look at concentrated sulfuric acid, you might remember in the alcohol lesson the concept of dehydration. So that means you have to remove the H and the OH. The trick to remember is that this carbon is going to lose the OH, and either of the 2 carbons can be used to take out the H. I could remove from here or from here. They both have the same number of H's, so it doesn't matter from which carbon you use to remove the H's. So I'm going to remove it from here. So if I do that, I will get Cl, CH, double bond, CH, CH2Cl. Don't forget the OH from here and 1 H from here is being removed, and that's why we get the double bond inside. For the next question, the next part, it says what happens when you react this with ammonia. Well, if you look at the compound again, we have Cl, CH2, CHOH, CH2Cl, and if I'm going to react this with ammonia, this question is from topic 16 of your syllabus, where you study halogen alkanes. You might remember that in halogen alkanes you could remove a chlorine and substitute with OH or NH2 or CN. So this is basically called nucleophilic substitution. Good to remember, it's a primary halogen alkanes. They basically undergo these kind of reactions. So all you have to do is remove the Cl from here and replace it with the NH2s. So you end up getting 2 of these. Now, in spite of the fact that they gave you ammonia, it doesn't mean that you only have to remove 1 Cl. Wherever you find the Cl, it has to be substituted, and you have to put NH2 there. So the correct answer now becomes NH2, CH2, CHOH, CH2, NH2. There you go. That's the answer to this question. This is question number 2. There is an equation mentioned. So 3NaNO3 plus 8 aluminium plus 5 NaOH plus 18 H2O gives us 3 NH3 and 8 NaAl OH4. Okay. Couple of other equations also given to help out with the ratios. If you look at the ratio between ammonia and H2SO4, it's 2:1, so we probably might be using it. So ammonia ratio H2SO4 is 2:1, and also the ratio between H2SO4 and NaOH also mentioned there as 1:2. So just keep a note on that. H2SO4 ratio NaOH is also 1:2. Okay. The first question says, calculate the amount in moles of H2SO4 present. Now, if you look at this question, you have the volume in cm3, which you must convert into dm3, and you also have concentration. So, using the concept of N equals to C times V, so I have the concentration 1.00, and I have the volume as 25. So I need to divide this by 1000 to change that into dm3, and that's how we get this answer 0.025. For the question A part 2, the question says find the moles of NaOH present. You still have the information about the volume and the concentration, so you still can use the formula N equals to C into V and work it out. So N equals to C times V. So I have the concentration as 2, and the volume is 16.2. But then don't forget, this is in cm3, so I can't use cm3. I need to divide this by 1000 to change into dm3, and this works to be 0.0324. That's basically how we get the moles of the NaOH. Now the next question says, using this information you are supposed to find out the moles of H2SO4 that do you think must have reacted with NaOH. Now don't forget, in the previous question you have the moles of NaOH, and now the question wants you to find the moles of H2SO4. So all you have to do is make use of that ratio. So to find the moles of H2SO4, connect this to the moles of NaOH. So from the equation given above, you know that between them the ratio is 1:2, and you already have the moles of NaOH with you, which is from the previous question, which is 0.0324. So you just have to put here x and cross multiply and just solve the value for x. So x will be equal to 0.0324 divided by 2, and that's how you get 0.0162 as your answer. That's how we get the moles of H2SO4. Now the fourth part of the question says, from the previous answers you need to work out how much H2SO4 is left to react with ammonia. Now what you must understand is, if you look at the answer of A1, the answer of A part 1, which you had 0.025, this was the moles of H2SO4 at the beginning. And then if you look at the answer of A part 3, which was 0.0162. Now this was the moles of H2SO4 that reacted with NaOH. So this was the initial moles, and then so much got used up. So now the questions for the fourth part says, find out how much is left. So all you have to do is subtract this from this. So the moles of H2SO4 left. So moles of H2SO4 left will be equal to 0.025 minus 0.0162, and that's how we get this answer as 0.0088. Now for the part 5 of this question, the question says, using your previous answer, try to find out how much moles of ammonia do you think will react with the acid. Well, the previous question that you solved, the answer that you got, the 0.0088, that was the moles of H2SO4 that reacts with ammonia. Now we know the moles of H2SO4 that reacts, and we know that between them, that's the ratio going on. From the previous page, there's an equation there. So if you just put all the values in, so my moles of H2SO4 is this, so that becomes X. So if I just cross multiply, obviously that will be 2 times that, so 2 into 0.0088, and that's how basically we get 0.0176 as the answer. Yeah, for part 6, now in this question they want you to find the moles of sodium nitrate in the alloy that reacted with the ammonia present. Now if you look at the equation, it's very, very clear. We have the ratio between them clearly mentioned as 3:3. So it's the same ratio there. So if you look at the ratio, NaNO3 ratio ammonia, it's the same ratio, so it's basically 3:3, or I could just say 1:1. It doesn't matter. Which means I have the moles of ammonia from the previous question, which is 0.0176, which means X also will be having the same value. So the moles of NaNO3 will be equal to moles of ammonia because this ratio is same. So that's why this answer also is 0.0176. For part 7 of this question, the question says, find the mass of NaNO3. Now, to find mass of any compound, you use the formula moles into mR. So I have the moles from the previous question, which is 0.0176. And I can use my periodic table to find out the mR of NaNO3, and that works out to be 85. So the final answer becomes 1.496 grams. That's how we figure the mass out. For the 8th question, the question says find out the percentage of NaNO3 present in the impure sample. Well, the formula to find percentage purity is always percentage purity. The formula is mass of pure over mass of impure times 100. That's basically how we find the percentage impurity. So if I look at the mass of pure, that's 1.496 from the previous question, and the impure is given as 1.64. So times it by 100, and that's how we get 91.2% as final answer. In B part, the question talks about calculation of oxidation numbers. This question is from topic 6 of your syllabus. NaNO3, the oxidation number of nitrogen in NaNO3. Now, don't forget sodium is in group 1, its oxidation number is +1, and oxygen's oxidation number is -2. Since it's a molecule, the sum of all oxidation numbers should be equal to 0. So that means this is 1 plus X plus -2 times 3, which is -6, should be equal to 0. And work this out, so it becomes X equals to +5. The oxidation number of N in NH3, similarly, since it's a molecule, the sum of all oxidation numbers is equal to 0. So this is X plus oxidation number of hydrogen is +1. So 1 times 3 is 3, should be equal to 0, which gives you X as -3. I'm going to pick up the question number 4 from the organic chemistry. Okay, this is the compound given. It's an alcohol, and normally when you start organic chemistry questions, it's always advisable to have a look in the question and see what groups do you have. So I have a primary alcohol, and I have an alkene, so it is useful when we have a look at this before we start. The first question talks about what happens if bromine reacts with it. Now, if you react with bromine, this is from topic 15 of your syllabus, you find electrophilic addition of bromine to alkenes. So one Br comes here and the other Br comes in here. So that's basically what happens. You get CH3, you get one Br here, you get another Br here. And this OH is not replaced by bromine, because if you want to do that, it can't work with bromine. You need HBr or PbBr3 to do that. So that's the answer for A. If you look at B, the reaction with PCl5, this is a reagent for nucleophilic substitution of alcohol. That means you can remove the OH and replace it with Cl. This is in topic 17 of your syllabus. So CH3, CH, double bond CH, CH2, Cl. That's the answer for this question. And now we look at part C. The question says add hydrogen to it. Now when you add hydrogen, this also is from topic 15 of your syllabus. This is electrophilic addition going on. So the two carbons with the double bond, they are the ones who will get the H added on to them. So the answer becomes CH3, CH2, single bond. The double bond now changed to single. One more H comes in here, and nothing happens to the alcohol. It remains as it is. Now, when you look at part D and E, now in part D it says react with NaBH4. Now that's a reducing agent, it's a mild reducing agent. It is used for reduction of aldehydes and ketones. Now if you look at aldehydes and ketones, you will find in topic 18 of your syllabus, now that's the thing is, this is alkene and that's alcohol. So none of this is aldehyde or ketone. That means there is nothing, there's no reaction which will happen here, there's no change. Both alkene and alcohol are not affected by NaBH4. If you look at this one, this is an oxidizing agent. So because it's an oxidizing agent, it will do the oxidation. Now we know alkene can get oxidized, we know alcohol can get oxidized, but the problem is alkene cannot be oxidized by dichromate. Alkene needs manganate to do the oxidation. Therefore, the only group which will be affected would be the alcohol group. And since there is no distillation being used, that means the reaction will not stop at aldehyde, it will continue to form the carboxylic acid. So just basically copy the whole thing out, just change that into carboxylic acid. So you get CH3, CH, double bond CH, and that changes to carboxylic acid. That's the only change. Now, the B part of the question says, react this compound with potassium permanganate, but it has to be in cold dilute conditions. Now that means this is low temperature oxidation for alkenes. Now, when low temperature oxidation happens, the double bond does not break. It remains where it is. The double bond changes into a single bond. And so you put one OH here, put one OH here, but interestingly, the primary alcohol cannot get oxidized in dilute conditions. It needs heat to do that. So that remains as it is. Just change this into the, that's where you put both the OH there. So the display formula becomes CH3, so you stick one OH here, and then you have another OH here, and that remains as CH2OH. So remember, primary alcohol cannot get oxidized under cold conditions with manganate. It needs heat to change into carboxylic acid. Now, part C of the question says, draw the skeletal formula of the compound formed in the reaction E. Now let's have a look what was in E. In E, this is what we got. CH3, CH double bond CH, COOH. So the examiner wants you to now convert this into a skeletal formula. Well, you should count the number of carbons. You have 1, 2, 3, 4. So 1, 2, 3, 4. That's usually how we do it. Each corner there is a carbon. There's double bond between 2 and 3. So 1, 2, 3. So there's a double bond between them. And then this carbon, since that's the carboxylic carbon, and I cannot show the carbon in the skeletal formula, but then I know my carboxylic looks like this. So I can't show this carbon, but the rest I have to show. So double bond O, bond OH. So that's the answer to this question. Now, for part D of this question, The question says, how would you confirm the presence of the aldehyde group which is present here? As you see, this has the CC double bond, which is the alkene, and it also has the CHO, which is the aldehyde group. Now, if you look at your topic 18 notes, you will have a lot of tests available for testing aldehyde. The good test could be, you could use a 2,4-DNP test, 2,4-DNP H test. The result of this test, that if aldehyde is present, you get your orange solid. You could also go for a tolerance reagent. Tolerance reagent, good to know, it's a solution of silver nitrate which contains ammonia. It's a mild oxidizing agent, so it gives a silver mirror test. So basically what happens is the silver ions present inside tolerance reagent change into silver, so they get reduced. So that's how it basically acts as an oxidizing agent. So there's a formation of a silver mirror that confirms the presence of aldehyde. You could also go for a Felling's reagent test. Felling's reagent is a solution containing copper 1 ion. So it's basically copper 1 chloride with ammonia solution in it. So it's ammonical copper 1 chloride, and this gives you the brick red solid which confirms the presence of aldehyde group. For question 4E part, the questions has given you some percentage composition of the compound, and it asks you to find the empirical formula. Now, to find the empirical formula, the concept is, if they give you percentages, you need to divide this by the respective AR, which means if you divide the percentage of carbon by the AR of carbon, by the AR of hydrogen, and by the AR of oxygen, and then you get answers. You get 6.14, 12.3, and 0.875. Once you have these numbers, the objective now is to simplify them into a simple ratio, bring them to a close to a whole number ratio. That means I need to divide all three by the smallest number possible, which is this one. So if I divide all of them by the smallest number, so we end up getting 7, 14, and 1. So this is basically the mole ratio that we're looking for, and this also helps us to find out the empirical formula, which means the empirical formula of this compound is now C7H14O. That basically is the empirical formula, C7H14O. Now, for question number 5, the question gives you the empirical formula as C2H4O, and it also gives you the MR, and it asks you what's the molecular formula of Q. Well, the procedure to get the molecular formula is supposed to be empirical formula times X. So to find the value of X, it's basically MR, which is always given, divided by empirical formula mass. Empirical formula mass. Now the empirical formula mass is the one that you calculate using the empirical formula, which is C2H4O. So you basically use the periodic table to find the value here, which is 2 times 12, which is 24, plus 4 plus 16, and that gives you 20 and 44. And then you put that value here, which gives you the value of X close to 2. Now you take that value and times it by the empirical formula to get the molecular formula. So the molecular formula becomes empirical formula times the value of X, which means it is C4H8O2, and that's the answer of this question. Now for part B of this question, it says, using the formula that you got above, work out the 4 different isomers of the of that molecular formula, and they should be esters. Now the formula that we got was C4H8O2, and you're supposed to make 4 different esters. A good way to start would be to keep in mind that esters, this is the functional group of ester. So if you want to make esters, you should draw a few of these and keep. So I'm going to draw 4 of these. So I know all 4 of them should have this functional group. I have seen many students, what they do is they try to make the esters from one end, and it usually doesn't work. The trick is to always make the ester group in the middle, and then try to place your carbons and the H's on either sides to fulfill the structure. In that way, you wouldn't be making much silly mistakes. Now, for example, I know I have 4 carbons. I put 1 carbon already. That means I have 3 carbons left. So I can put 1 carbon, or maybe all 3 carbons here, and I can just put an H. So, so that would be, I'll just make it a bit more closer. So I can put my 3 carbons here. That's it, that's my first ester there. So let's say I label this as W. In my second ester, maybe I want to put only 1 carbon there, or 2 carbons there. So I put my 2 carbons here. So CH2, CH3. My third carbon is here, which means I only have 1 carbon left, and that I can put it here, and that's going to be my second isomer, X. So I put 3 carbons, I put 2 carbons. Now the option which I have is I can put 1 carbon. So I put 1 carbon there, so that's a CH3. That leaves me with 2 carbons, so I'm going to put my 2 carbons here. And that's my third ester. I'll just label this as Y. Now the challenge to make the 4th isomer is to think of chain isomerism that you studied in topic 14. Now that teaches you that you could change the parent chain here. So that means instead of 3 carbon, I can make 2 carbon chain. So it will look like this. And I can hang 1 carbon down here. And so that's 1, 2, 3, 4. There you go. So all my, if you check your molecular formula, you must check for each one whether it fulfills the molecular formula or not. That is my Z. So basically I have now 4 different isomers of this compound. Now on page 11, the second part of the question says the ester Q was hydrolyzed using sulfuric acid. Now that means that the ester link, which is this, is going to get broken here. And it is going to change into, this bit is going to change into the carboxylic acid, and that bit, whatever is there, is going to change into the alcohol. And once it happened, after the split happened, the resulting mixture was then reacted with dichromate. It means the alcohol part, which will come from here, is the one who's going to get oxidized by dichromate, which means clearly it can't be a tertiary alcohol, because they cannot be oxidized. It has to be a primary or a secondary alcohol. But then the question goes on and says, it must give you a single product. That means whatever acid this will give you, the same acid you should get from the alcohol from this side. That's what the question talks about. And there are some further hints given. It says the product R, which is formed after the dichromate's reaction, should not react with Tollens reagent. Well, if it doesn't react with Tollens reagent, that completely rules out aldehydes. And then it should not react with 2,4-DNP as well, which clearly means it cannot be ketone as well. And the third hint gives you that it does react with sodium carbonate. Now we know sodium carbonate can't react with alcohol, that for sure it reacts with carboxylic acid. So that's the evidence that R is a carboxylic acid, and R cannot be aldehyde and ketone. So if you look at C1, it says what does the result of the test with Tollens reagent show about R. So it means if you could write an answer of C1 as aldehyde group is absent. So C1, you could say aldehyde is absent You could check the test of aldehydes and ketones in topic 18 of your notes there. The second part talks about what do you think, what is the result of the 2,4-DNP test tells you. Well, if it doesn't react with 2,4-DNP, it means it cannot be aldehyde or ketone. So, but then aldehyde ketones basically have carbonyl group. So this question was basically asking about what functional group. So whenever they ask you functional group, always say carbonyl group is absent. That's the thing what they were looking for. So basically this, which is your carbonyl group, is absent. Good to know 2,4-DNP is also called as Brady's reagent. The third question talks about what functional group do you think is present because it reacts with sodium carbonate. Clearly it means there is carboxylic acid. So the third question answer is carboxylic acid present. For question 5, D1, it says, what is the identity of the single organic compound R? Now, as I was talking earlier, if you look at an ester group and you break it this way using acidic hydrolysis, it is supposed to give you a carboxylic acid and this part is supposed to give you an alcohol, but that's when you do acidic hydrolysis. So when you do acidic hydrolysis, the ester is going to split and give you these two. Now since the question said the resulting mixture was further reacted with dichromate, that means this alcohol has got oxidized, which clearly means it can't be tertiary alcohol, it has to be primary or secondary. Now the issue with secondary alcohol is, secondary alcohol on oxidation gives you a ketone, and that is not ketone. So which clearly means I cannot be looking at an ester who will probably give me a secondary alcohol. So what you could do, you could look at your isomers, what you made in the previous page, and check which isomer has equal number of carbons on both sides. So you're probably looking at an isomer which must have 2 carbons here, and it must have 2 carbons here. So when you break this, this changes into ethanoic acid, and that changes into ethanol. And when you oxidize ethanol, it then changes into ethanoic acid. So both the acid is the same thing. So you get ethanoic from here and you get ethanoic from there. So that's why the answer of the first question is ethanoic acid. And to figure out which ester is going to give you that, so if you turn the page, just try to check which of your 4 isomers was this one. And that's the answer that you'll write here. For the last question, which talks about which of the 4 esters you made could be a chiral. Now, the thing about chiral carbonate, it must have clearly 4 different atoms or groups attached on it. But if you look at all the 4 isomers that you made on the previous page, you will find there is no chiral carbon present. So actually none of them can show any optical activity. Well, that's it, student. That was my first video of the CIE past papers for AS paper 2. I do hope to make more videos of such kind. This is the first video, so I'll try to improve on the quality of sound and lights and as I learn how to make them. I hope you enjoyed it and I hope you liked it, and don't forget to give me some feedback in comments, and if there's anything I can improve, please let me know. Ciao.